So if you think back to before you were in calculus, and what kinds of skills did we practice with functions? One of those skills we practiced was, can you substitute values in and get outputs that come out of it? But graphing or sketching the graph was definitely one of those skills. And this isn't really a new topic in what we end up doing in a moment, but it is a new topic by the way it looks on the paper and by the way we name the directions maybe. So if we were to want to sketch the following function, first of all, if it were in my classroom, I wouldn't expect you to know what this is just by first time ever observation. However, this may not be our first time observing this. If we think about looking at this problem as z equals x squared plus y squared, well then I might remember that that is a paraboloid or a parabola bowl. It opens in the positive z direction and it keeps going up forever. That would be the z-axis. And in the xy cross sections you would see circles that get bigger the higher up you go. So we could graph that if it matches its z equals sort of look without me doing any additional instruction right now. Now if you haven't practiced graphing in 3 variables, you could go back to one of my earlier video segments on doing just such a thing, and there are many other tools out there for learning how to sketch those types of functions with 3 variables. So, what if it was this? What if it was simply z equals 2? What is that graph? What does it look like? Here's x, here's y, here's z. Well, what it's saying is that no matter which pairs of numbers you give for x and y, let's write it this way. Z's 2, no matter what. I mean, it says here, z is always 2. You can choose any other x and y you want, but z is going to be 2. Well, what this looks like is every point in space that is 2 units above the ground. And so how you draw this, oh, there's so many ways of looking at this. We need to imagine a plane that is 2 units above the xy plane. I'm not sure how good my picture is going to look here. I don't know. Give it a whirl here. We'll just pretend that's the point where it punctures through the plane. If you've seen some of my other instruction videos, this is not actually a graph. I would say to my students, you need to graph this or else. If there were 3D models available, I do expect them to be able to pick it out of a lineup. Aha, that's the graph that goes with z equals 2. Let's meet a couple of more. One of them is a familiar graph in disguise. The second one, well, we'll get there. So, let's see what we can do. All right. So we're going to look at this as z equals 6 minus x minus 2y. And my initial thought about this is, I don't know if I've ever met it before. I don't know you. But think of this as an actor or actress who has such a significant makeup or costume job that you don't recognize them. If I were to add x to both sides of this equation and add 2y to both sides of this equation and rewrite it, this, my students and my visitors, is a plane. And we used intercepts to sketch planes. This is the type of plane I did hold my students accountable to. Right, y, z, x, okay. And if you do some calculating here, you'll find that if x is 6 and y and z are both 0, you have a point out here on the x-axis. If x and z are both 0, you would need y to equal 3 for this to add up to 6 altogether. So that was 6, and this is 3. And then finally, if x and y are both 0, z would have to be 6 in order to satisfy this equation. So that would be a 6 right there. And instead of drawing the plane in a rectangular form, any flat surface that you could think of that fits on a piece of paper could serve as your plane. In this case, the triangle works great. So this is the representation of a plane, and the coefficients 1, 2, 1 in front of these variables represent what was called the normal vector that is orthogonal to every vector on the plane. It is called normal to the plane. One more to go in this segment. Remember, you do have a pause button, and you can go back and catch up if I just went too fast. Okay, z equals square root 9 minus x squared minus y squared. I'm not sure if this looks familiar to me. So I'm going to do some algebra manipulation. I'm going to square both sides, and I'll have z squared equals 9 minus x squared minus y squared. Yes, I know I just did something a little bit fishy, but don't worry, I'll come back to it. And let's add x squared and add y squared to this side. You recall what that is? That is a sphere. That is a sphere. That sphere of radius is 3. That sphere that would look like this. And it would be like this, and there's the z-axis, and the center's down here, and there's the x-axis, and there's the y-axis, and the radius is 3 wherever we look. And then I would tell you that that's not the correct graph. It's wrong. You heard me. It's not correct. There is something not right about this. In my efforts to make the equation something I could recognize, I did some damage. This here, z equals, would only be positive in this form. The square root only generates positive outputs. That's because it's a function. It has one output. So what would it look like if this graph only had positive z values? Well, that is a hemisphere. It is the top half of this same sphere. Z, X, Y, radius is 3 still. You could call it the upper hemisphere if you want to, as long as everybody has the same orientation for up and down. That's a 3 right there. This graph is the correct graph. It is the positive z values. I probably could generate other hemispheres if I solved for x or for y. But this one was solved for z equals. So it would be the upper hemisphere. Not this one, but this one. Now, just like before, there's a limited number of graphs I would have you know from memory if you're sitting in my classroom. And there are more we could generate with some software help. And then there's the infinitely more that follow that maybe we can't always graph. That is one of the reasons the calculus will be there for us. It helps us study things that we cannot see. But if that doesn't sound familiar to you, well, we'll get there eventually. Until next time.